Calculus is one of the greatest ideas in human history, yet remains one of the most misunderstood. The very mention of calculus often creates an aura of fear, as if it is impossibly difficult. But the real problem lies in how it is taught, memorized instead of understood. For many students, calculus becomes a set of rules to follow rather than ideas to explore. In this story, I want to show that calculus is more than formulas. It can be an adventure of understanding. Meet Mafta. She is a cook and a meat seller, famous for her delicious seasoning. Suppose the grams of seasoning Mafta uses follow the model. Grams equals pounds of meat squared. In symbols, y equals x squared. If Mafta normally buys x pounds of meat, and now she wants to add an extra dx pounds, the new amount is x plus dx, and the new grams of seasoning are y plus dy, where dy is the amount she should increase her seasoning by to preserve the original flavor of her meat. Plug that into the model, you get y plus dy equals x plus dx squared. Expand, and you get y plus dy equals x squared plus 2x dx plus dx squared. Since y equals x squared, we obtain the exact relation. dy equals 2x dx plus dx squared. That formula is exact. It tells how the seasoning must change for any finite change in the pounds of meat. However, traditional calculus introduces a simplification. When dx is infinitesimally small, the dx squared term becomes negligible. So, the differential estimate becomes dy is almost equal to 2x dx. If you divide both sides by dx, you get the limiting ratio, which we call the derivative. But beware, that linear estimate only works when dx is very small. For example, if Mafta starts with 20 pounds and must increase by 50 pounds, the exact change is dy equals 2 times 20 times 50 plus 50 squared equals 4,500 grams of seasoning. Using the linear approximation alone yields dy is almost equal to 2 times 20 times 50 is equal to 2,000 grams of seasoning, which is far from the true value, for 1,500. However, if dx equals 0.00001, both formulas give virtually the same answer. That is the idea behind taking limits. Now, what if we only know the amount by which Mafta's seasoning changes when the pounds of meat change by a very small amount? How can we create a model that tells us how much seasoning Mafta needs when she buys a certain number of pounds of meat? Let's think step by step. Each tiny increase in the pounds of meat is called dx, and each tiny increase in seasoning is called dy. The total pounds of meat is the sum of all the dx's, and the total seasoning is the sum of all the dy's. This is exactly where the concept of integration comes in. We begin with the linear approximation, since we are considering a very small change. dy equals 2 times x times dx. If we add up all these small pieces, we get a summation. The sum from k equals 0 up to n minus 1 of f of k times dx multiplied by dx, where n equals x divided by dx. In other words, how many tiny pieces make up Mafta's pounds of meat. Substituting, we get the sum of dy equals 2 times dx squared, multiplied by the sum of k. Here we use the well-known natural number formula for the sum of k. The sum of k equals n minus 1 times n, all divided by 2. Simplifying, this gives an approximate relationship. Y equals x squared minus 3 times x times dx plus 3 times dx squared. Now, here's the key assumption behind integration. If dx is very small, those extra terms vanish, leaving simply y equals x squared, which is Mafta's previous seasoning model that relates her grams of seasoning to her pounds of meat. But even without taking a limit, we can also show that summing 2k times dx plus dx squared gives us exactly y equals x squared. That's the heart of integration, adding up infinitely small changes to build an exact model of the whole.